Engineering kinematics provides the tools to predict the exact future state of a moving object based on its current behavior. We start with the basic definition of acceleration, the rate of change of velocity over time. As the top box shows, if acceleration is constant, we can integrate it over time to find a standard velocity formula. Moving down, a second integration gives the object's displacement, establishing a mathematical relationship between position and time. By algebraically eliminating time or acceleration from these results, we can derive equations 8 and 9, completing a baseline toolkit of 4 standard equations of motion. This summary displays the SUVAT toolkit, an acronym for displacement, initial and final velocity, acceleration, and time. Its utility lies in flexibility. As the concept check highlights, it allows engineers to calculate a future state by bypassing variables they don't know. These formulas offer a reliable baseline, but they share a single point of failure. They rely on the absolute assumption that acceleration remains constant. In advanced mechanical systems, forces are rarely constant. They fluctuate based on an object's precise position or its speed as it moves through a fluid. When an industrial shock absorber compresses over uneven terrain, the resistive force changes every millimeter, meaning the acceleration is never a single flat number. Applying standard formulas to non-constant systems leads to the variable acceleration trap. On the left, algebra works perfectly if acceleration remains a flat, unchanging line. But on the right, if forces cause acceleration to curve, algebraic shortcuts produce mathematically impossible results. There are no algebraic shortcuts for dynamic, fluctuating forces. To solve real-world engineering problems, we have to move beyond these static formulas and rebuild our predictive model using pure calculus. This presents a central problem. How do we calculate acceleration if we only know an object's position, but lack any data regarding the time it took to get there? The center panel provides the solution. We rewrite the core definition of acceleration using the chain rule, a method for differentiating a function of a function. On the second line, we split the time derivative, dv by dt, introducing a spatial derivative, dx. We then substitute dx by dt for velocity, v, because velocity is the rate of change of position. This results in the final green equation. We have successfully expressed acceleration without using time. This blue box establishes the golden rule. The form of acceleration used is dictated entirely by the independent variable presented in your data. We can test this spatial derivative on a classic system, a mass on a spring, defined by its kinetic and potential energy. In step 2, differentiating this energy equation with respect to position uncovers the underlying acceleration. By step 3, the calculus isolates a velocity gradient term. Substituting our new definition shows the math is consistent, matching Hooke's law for elastic forces. Now we apply this to heavy industry. This diagram analyzes a pile driver, a machine driving foundations. In part B, we build a custom equation of motion from scratch using Newton's second law. Net force equals mass times acceleration. The constant weight of the pile is canceled out by the upward support of the Earth, leaving only the complex, position-dependent resistive force of the ground. Looking at this final mathematical expression, the resistance depends on the position, x. This means we must use the v dv by dx form of acceleration to correctly prepare for integration. By combining Newton's physical laws with the correct differential form, we can mathematically model any mechanical scenario, no matter how chaotic the forces become. We can now evaluate the ultimate kinematic test, tracking the exact trajectory of a lighter-than-water object plunging beneath the surface. The exact moment the heavy object violently hits the dark water, it experiences an immediate, chaotic conflict between several opposing physical forces. This free body diagram shows a constant net buoyancy pushing upward, fighting against a velocity-dependent drag force pulling it down. In the top right equation, we map these opposing forces onto Newton's second law to establish the raw equation of motion. We insert the numerical values for mass and water resistance, simplifying the math to reveal this final boxed equation governing the entire descent. This single differential equation defines the entire underwater descent. To extract specific values for time or displacement from it, we must choose the specific calculus form that matches our target variable. Our first goal is to calculate the exact time it takes for the object to reach its maximum depth. Because our target variable is time, we swap acceleration for the time derivative, dv by dt. We apply boundary conditions from the table, setting limits from surface entry to full stop. Integrating this setup yields the duration. The object stops in exactly 1.57 seconds. Now we pivot to the second goal, calculating the exact maximum depth the object achieves. Setting time aside, we swap a for our spatial derivative, v times dv by dx. We apply the same boundary states to set the limits for this position integral. Resolving the integration gives the absolute distance traveled. The object sinks 2.77 meters. This summary dashboard shows the results of both paths. We have decoded a single physical event into two distinct predictions using different branches of calculus. Solving advanced kinematics requires translating these physical forces into differential equations. By applying different forms of calculus to the same model, engineers can accurately predict the behavior of complex systems where simple algebra fails.